In this video, we will be looking at my code on how OpenCV works with things like this. These are ArUco Markers. So I'm part of my university rover team, and alongside object detection for the movement of our rover, ArUco Markers play a huge role for the autonomous navigation, especially, or map-based navigation, whatever you say. And in this video we'll have a look into how you can actually use the ArUco Markers to measure distance. Like, that's the first step of the map-based navigation system. So let's get started. Okay, so in this code we're supposed to make 5x5 ArUco Markers, like generate them through the code. We can also achieve the same stuff from online.
Okay, so yeah, this one has market deduction. Here, cd generate markers, that's the folder name.
Now we can run Python main.py. Cool. So this is our ArUco Marker 5x5. Now we will be generating into this, like 20 of them into this empty folder. Yeah, as you can see, we only have this one. We are supposed to have 20, as many as we want, but we will generate 20 for now. So to get the 20 5x5 markers that we want, we just comment out this, because last time I just wanted you to see how one marker is generated. So yeah, with that, I guess Control S, I save the file and run it. And as you can see, we have 25x5 markers starting with 0 to 19. Yeah, so yeah, for the marker generating part, that's it. And for the detection, we can start here, a different file. Let me get my ArUco Markers 5x5. Yeah, okay. Okay, as you can see, these are giving proper IDs for number 1, number 4 together in a list. Number 1, 4 together. Yeah, 1, 4. And if for this code, let me just interrupt with Q. Nice. And for this code, it should give proper IDs. Sorry for the brightness. Yeah, it works perfectly until I take it too far away. And when my camera was detecting this cube, it could do it until 8-9 feet only when the borders were clear. So I realized the corners were really important. And now for the camera calibration, we'll be relying on a 9x6 chessboard design. You can find the pattern from OpenCV's website, or any chessboard design would actually work. And the goal is we want to train our camera not to take distorted photos and gaining accuracy. So let's get into the code. And if you want to play with my code on your own compiler, make sure you visit my GitHub. So yeah, and as you can see, we have 2 frames. One is the copy frame on the right side, and the left side will have the augmentation, of course. And you can see the photo saving count. So yeah, all the images are stored into the path we specified in the code. As you can see in the folder, we have all the pictures. The 9x6 dimensions are pretty visible. Now, to access the calibration data, we will import the OS module and numpy, and with the SaveZ function we will get several arrays into one single file, uncompressed, as you can see, the .npz format, which contains all the object points and image points in a more readable matrix form. Now let's check if our code works or not, and that if we could measure real-time distance with it. The distance was accurate until I took a diagonal perspective, at least not straight from the camera, and the accuracy was dropping to 70 to 75%. But then again, with only 20 photos and the crappy calibration data that resulted in, I'm pretty much happy with what we got. And if you still want more accuracy, you could definitely put in more photos for your reference to get better calibration data, better accuracy, and you can definitely change the algorithm in your way. You could definitely visit my GitHub for that. That said, I'm pretty much hopeful to make more contents like this, so would love it if you listen to Mr. Crab, because he says you should definitely subscribe to this channel. And you should also listen to Mrs. Crab, because she says you should definitely like this video to help me with the algorithm. And you should definitely listen to the couples, because you know what? If you don't listen to them, they might come in your bed at 3 a.m. You just don't know. So yeah, that said, goodbye.